Welcome to the May 2025. This is the Core Pure 2 paper walkthrough from the Further Maths A-Level. Alright, let's crack right on. Question number 1. This one is about performing the calculations with the complex numbers. So to show that the modulus of z over w is equal to the modulus of z divided by the modulus of w, we'll just calculate all of those values. To divide by -1 plus root 3i, multiplied by its conjugate, that's -1, subtract root 3i, over -1, subtract root 3i. Carry out your double bracket expansion, -2 minus 2 root 3i plus 2 root 3i, subtract 6. The complex parts will cancel, and we're left with -8 over 4, which is -2. Then the modulus of z, using Pythagoras, it's going to be the square root of 2 squared plus 2 root 3 all squared. That comes out as the square root of 16, which is 4. So the modulus of z is 4. For the modulus of w, we've got -1 squared plus root 3 squared, all square rooted. And that comes out as 2. That's sufficient to show what we want to show. So the modulus of z divided by the modulus of w is 4 divided by 2, which is 2, and that is the same as the modulus of z over w. Okay, for part B, the argument of zw, is that equal to the argument of z plus the argument of w? Well, we'll work out each one of them. So zw, z times w, 2 minus 2 root 3i times by -1 plus root 3i is the same as -2 plus 2 root 3i plus 2 root 3i plus 6. Or if you prefer, 4 plus 4 root 3i. Okay, so to find the argument of zw, well, it's in the top right quadrant, so we can just do inverse tan of 4 root 3 over 4, which is pi over 3. For the argument of z, we can do inverse tan of -2 root 3 over 2 in the bottom right quadrant. So it comes out as minus pi over 3. For w's -1 plus root 3i, so it's in the top left corner of the argon diagram. So I'm going to do the trig to find the angle on the right angle triangle that's formed there, and then subtract that from pi to find its argument. So it's pi subtract inverse tan of root 3 over 1, which is 2 pi over 3. And if we add together the arguments of w and z, we do indeed get the argument of wz. And that's question number 1. Question number 2 is a vectors question. So for part A, we want to find the shortest distance that the arrow must travel to reach the plane. So I'll do a quick rearrangement of the equation of the plane. Then we can use the formula for finding the shortest distance between a point and the plane. So we multiply 3 by the 2, the -5 by the 4, the 2 by the -1, and then subtract 3. And we'll divide that by the square root of 2 squared plus 4 squared plus -1 squared. Plug that all in, and we get 19 lots of root 21 all over 21. That's our shortest distance. For the equation, the vector equation of the flight path of the arrow, well, it's going to be the position vector plus scalar multiple of the direction vector. So we've got 3, -5, 2 plus lambda lots of 3, 3, -1. The 3, 3, -1 comes from the difference between the two position vectors, 3i to 6i minus 5j to minus 2j and 2k to k. Part C, we're finding the angle between the vector, the direction vector taking the arrow, and the normal to the plane. So using the cosine version, we'll have cos of the angle between them will be a dot b over modulo a times modulo b. Plug them all in, and we get 19 over root 19 times root 21. So calculating inverse cos of 19 over root 19 times root 21, that comes out as 18 degrees. That's the angle between the flight path of the arrow and the normal to the plane. We want to work out the angle between the flight path and the target itself. So that's sort of the plane itself. So I'm going to subtract that 18 from 90 degrees to get the 72 degrees, which is my final answer. For D, we've already done this calculation in the previous part, but just applying Pythagoras between the distance between the 2 points, square root of 3 squared plus 3 squared plus 1 squared, which is root 19. For part E, well, the flight path is not going to be a straight line because there are things like gravity, which will, and air resistance, and all the other factors that will feed into projectile motion in the real world, which this model ignores. So it is likely that the actual distance will be slightly longer. Perhaps the flight path will be slightly parabolic, or at least close to a parabola, and so the actual distance of the flight will be greater than the one we've calculated here. Question number 3, it's a proof by induction question. So I shall begin by considering the case when n equals 1. This is the pushing over the first domino. Some people prefer to set up the inductive process first and then push over the first domino. I'm not sure it really matters. Anyway, when n is 1, we're going to get the matrix 1, 5 lots of 2 to the 1 minus 1, 0, and 2 to the 1, which is indeed 1, 5, 0, 2. So that works. We will assume that it is true for n equals k. That is, we are going to assume that a to the power of k is equal to 1, 5 lots of 2 to the k minus 1, 0, and 2 to the k. And we're going to consider the case when n is equal to k plus 1. Well, a to the power of k plus 1, that's going to be equal to a to the k times by a. Now we've assumed that a to the k is 1, 5 lots of 2 to the k minus 1, 0, 2 to the k. So we'll take we'll take that and multiply it by 1502. Carrying out the matrix multiplication, we're going to get 1. And then we've got 1 times 5, and then 5 lots of 2 to the k minus 1 times by 2. So I'll call that 10 lots of 2 to the k minus 1. The bottom left, you're going to have 0 times 1 plus 2 to the k times 0. In the bottom right, that'll be 0 times 5, and then 2 to the k times 2, which is 2 lots of 2 to the k. All right, now all that remains for us is to turn this into the matrix that we want. So I'm going to expand out the 10 lots of 2 to the k minus 1, and I'm going to rewrite 2 times 2 to the k as 2 to the power of k plus 1. Then concentrating on the top right, we can split 10 up into 5 times 2, and the 5 subtract 10 is minus 5. And that allows us to factorize the top right. So we can factorize out a 5, and we can do the 2 times 2 to the k as 2 to the power of k plus 1. And we now have it in the desired form. So we can see that it's true for n equals k plus 1. We've now set up the inductive process and finish off with a statement. We know it's true for n equals 1. We've tested that when it works. And when we assume it's true for n equals k, it turns out to be true for n equals k plus 1 as well. That's the fundamental structure of any proof by induction, and therefore we've proven that it's true for values of n that are 1 and above the natural numbers. Okay, for part B, minus 1, 0, 0, 1. That's a reflection in the line x equals 0, or a reflection in the y-axis if you prefer. Part C, if we multiply our expression for a to the n by b, we'll get our matrix C. And so we're just carrying out a simple matrix multiplication there. Gives us a minus 1 at the front. So minus 1, 5 lots of 2 to the n minus 1, 0, and 2 to the n. For part D, if we multiply that matrix by 27, 1, we get the point AA. So we've got negative 1 lots of 27 plus 5 lots of 2 to the n minus 1 times 1. That's going to be equal to A, but A is also equal to 0 times 27, plus 2 to the n minus 1. So our minus 25 plus 5 lots of 2 to the n minus 1 will be equal to 2 to the n. Expand that out, bring the 2 to the n's on the left and the non-2 to the n bits to the right. We get 4 times 2 to the n is 32, so n is equal to 3. Substitute that into our matrix. That's our matrix for A. When n is 3, we get 1, 35, 0, 8. Question number 4. Because z1 plus z2 is real, we know that d must be equal to minus b, and we can replace all of the d's with minus b's. We know that modulo z1 is root 13, so a squared plus b squared is 13. Similarly, c squared plus b squared will be equal to 25, because modulo z2 is equal to 5. Subtract c squared from both of those, b squared is 25 minus c squared. Then going back to the a squared plus b squared equals 13, we can replace b squared with 25 minus c squared. We know that c minus a must be equal to 2, because the real part of z2 minus z1 equals 2. And so c must be equal to 2 plus a. Replacing the c in the a squared plus 25 minus c squared equals 13 equation with 2 plus a, we get an equation, a quadratic in terms of a, and that will unlock the question for us. So expanding out the 2 plus a squared, and then cancelling everything that cancels. And then solve that in any way you want to. As long as it's correct, you'll get a equals 2. You can therefore deduce c equals 4, b will be 3, and d will be negative 3. Okay, for part 2, so the locus of points which satisfy the two equations, these are going to be circles. So here's my Argand diagram. The z subtract 12 is equal to 7. Well, that's going to be centered at 12 on the real axis. And we're going to get a circle that's got a radius of 7 traveling around there. So it's going to intersect the real axis at the points 5 and 19. For the circle W, it's going to be centered at 5i. So that's 5 on the imaginary axis. And it's got a radius of 4, so it's going to cross the imaginary axis at I and 9i. There's 1 and 9 on that imaginary axis. And there are our two locus of points. For part B, well, if we draw a straight line between them, we'd get a little right angle triangle. So the length of that, the distance between the two centers is going to be the square root of 5 squared plus 12 squared, which is 13. Then we could add the two radii or subtract the two radii to find the minimum and maximum distance range of those possible values. When you subtract the two radii, you get 2. When you add the two radii, you get 24. So we're looking at values here between 2 and 24. And that's question 4. Question 5. If we turn this into a 3 by 3 matrix, the determinant of that matrix will be equal to 0 when these form a sheaf. So I'm going to calculate the determinant of the 3 by 3. That's 2 minus 1, 1. 1p minus 3 and 3, 1 minus 2. So here I am applying the standard algorithm for finding the determinant of a 3 by 3, equating it to 0, and then solving the equation to find p. 1, it's straightforward. And we get p equals 2. For part 2, I'm going to take the first equation, I'm going to take the second equation, and I'm going to add the two together. So 2x minus y plus z equals 3, and x plus 2y now, because we know that p is 2, x plus 2y minus 3z equals q. If I add those two together, we get 3x plus y subtract 2z is equal to 3 plus q. And if I compare that with the third equation, 3x plus y minus 2z equals 4. Well, from that we can see that we're going to get a sheaf when q is equal to 1. If it's not, then we're going to have something very different. So q equals 1. Question 6. So the sum and product of roots question. The first thing I'm going to do is take the quartic equation, divide everything by 2. So x to the 4 plus a over 2x cubed, subtract a over 2x squared, subtract 5 over 2x plus 3 equals 0. Okay, for a, we want to determine the value of 3 over alpha plus 3 over beta plus 3 over gamma plus 3 over delta. And so to add those fractions together, we're going to need a common denominator. So the only common denominator that's sensible here is going to be alpha, beta, gamma, delta. So we need to take 3 over alpha, multiply top and bottom by beta, gamma, delta. So we get 3 lots of beta, gamma, delta over alpha, beta, gamma, delta. And then we're going to do that the same with all 4 fractions. Add them together once we get the common denominator, and I factorised a 3 out the front just to save me writing it lots. So we've got all the combinations of what we're multiplying the top and bottom by for all four fractions, and that's going to be over the common denominator alpha, beta, gamma, delta. Okay, so the product of the combinations of 3, the sum of those is going to be negative the value in front of the x, so negative 5 over 2. So we're going to get 3 lots of 5 over 2 over the product of the roots, which is going to be 3. So 3 times 5 over 2 over 3 is equal to 5 over 2. I don't know why I wrote 3 as 6 over 2. There we go. Maybe I'm thinking it might cancel with the 2 at the top. Anyway, for part B, alpha plus beta plus gamma plus delta, if I consider squaring that, we'd get the alpha squared plus beta squared plus gamma squared plus delta squared plus 2 lots of all of the other pairs of combinations of numbers from those, so six of those pairs. Alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta plus gamma delta. Well, the sum of the roots is going to be a over 2. So the sum of the roots squared is going to be a over 2 all squared. It tells us, it's given that the sum of the squares is negative 3 over 4. And then the product of the pairs, alpha, beta plus alpha, gamma, etc., is going to be negative a over 2. So a over 2 squared is equal to negative 3/4 plus 2 lots of negative a over 2. And now we're dealing with a quadratic equation in terms of a. Square the a over 2. 2 lots of negative a over 2 is negative a. I've times everything by 4 here. Brought it all onto the left hand side. A squared plus 4a plus 3 equals 0. That one factorizes nicely. A plus 3 and a plus 1. That's equal to 0. So our two values of a are negative 3 or negative 1. Okay, question number 7. So we have the polar equation. We want to use calculus to determine the polar coordinates of A and B. Those points A and B are going to be when the x-coordinate, the change in the x-coordinate as theta changes is 0. So finding an expression for the x-coordinate is going to be r cos theta. So we can take our equation in terms of r, multiply it by cos theta. So r we know is a lots of 1 plus sine theta, so times that by cos theta. I've expanded that out, so a equals a cos theta plus a sine theta cos theta. Then we want to find dx by d theta, how the x-coordinate is changing as theta changes. So differentiate a cos theta, you get minus a sine theta. And then the product rule for the second one is going to be a lots of cos squared theta subtract a lots of sine squared theta. So our 2 points A and B are the points where dx by d theta is 0. So 0 lots of, and then what we had before, I factorized out an A from that. I could have divided by A here because we know that A is not 0. But I didn't. I saved it for one more though. Using our cos squared theta is 1 minus sine squared theta. So cos squared theta minus sine squared theta becomes 1 minus 2 sine squared theta, then minus the sine theta at the end. Finally got rid of the A, did a little rearrangement, made the coefficients of sine squared theta positive by multiplying everything by -1. And we get a nice quadratic in terms of sine theta, which factorizes nicely to 2 sine theta minus 1 and sine theta plus 1. So we can extract out our values of theta. We're going to get sine theta equals 1/2 and sine theta equals -1. The sine theta equals -1. If we substitute the values of theta we get out from that, we quickly see that that's actually dealing at the point O, not the points A and B. So I'm going to park the sine theta equals -1 and just look at sine theta equals 1/2. There's two values of theta for that one. There's theta being pi over 6 or 5 pi over 6. In both cases, to calculate R will be a lots of 1 plus and then sine theta. So sine theta is 1/2, so it's a lots of 1 plus 1/2, which is 3 over 2a. So our polar coordinates of A and B are going to be 3 over 2a when theta is pi over 6 and 3 over 2a when theta is 5 pi over 6. Okay, for part B, well, the x-coordinate of A, we know we can get from doing our cos theta, it's the same as in part A. So substituting in our pi over 6 for A, we're going to get a lots of 1 plus sine pi over 6 times by cos of pi over 6. We know that sine of pi over 6 is 1/2. Cos of pi over 6 is √3 over 2. So our x-coordinate at A is going to be a lots of 1 plus 1/2 times by √3 over 2, which is 3 √3 over 4 lots of A. Doing exactly the same with our point B, finding the x-coordinate of point B, we're going to get a lots of 1 plus sine 5 pi over 6 times by cos of 5 pi over 6. So this time we've got a lots of 1 plus 1/2 times by, well, cos of pi over 6 is negative √3 over 2. So our x-coordinate of b is minus 3 root 3 over 4 lots of a. Now it tells us in the question that the distance between these two is 10. So if I subtract one from the other, we get 3 root 3 over 4 lots of a, subtract negative 3 root 3 over 4 lots of a. That's going to be equal to 10. So 6 root 3 over 4 lots of a equals 10. Times both sides by 4. Divide both sides by 6 root 3. A is equal to 40 over 6 root 3. I've cancelled the 2, 20 over 3 root 3, rationalise the denominator, 20 root 3 over 9 is the value of A, which is what the question wanted. For part C, we can find surface area by doing a half of the integral between minus pi and pi of r squared d theta. So that's a half the integral between minus pi and pi of a squared times by 1 plus sine theta all squared d theta. We know a, so we can square it. If we square a, we get 400 over 27. And expanding out the 1 plus sine theta all squared will be 1 plus 2 sine theta plus sine squared theta d theta. I'm going to take the constant out the front, so half 400 is 200, so 227. Lots of the integral between minus pi and pi of 1 plus 2 sine theta. I'm going to replace sine squared theta with a half minus a half cos 2 theta. You could integrate it using integration by parts twice if you wanted to, but it's easier to do it this way. So it's 227ths of integrate 1 plus a half is 3 over 2, so 3 over 2 lots of theta. 2 sine theta integrates to minus 2 cos theta. And then we're going to get subtract a quarter sine of 2 theta between minus pi and pi. Substituting those into the integral, I'll leave the 200 over 27 at the front, so 3 over 2 lots of pi. Then cos of pi is minus 1, so add 2. And then plugging negative pi in, we're going to subtract, it's going to be negative 3 over 2 pi plus 2. The plus 2's will cancel, we'll get 3 over 2 pi, subtract negative 3 over 2 pi, which will come to 3 pi, so it's 227ths of 3 pi, which is 200 pi over 9, and that's the surface area. Question number 8. This is the hyperbolic equation. All right, differentiating using the product rule, cos x differentiates to minus sine x, so minus sine x, and then hyperbolic sine of x. Hyperbolic sine of x differentiates to hyperbolic cos of x, so we get cos x times hyperbolic cos x using the product rule. Then using the product rule again, minus sine x differentiates to minus cos x. And then hyperbolic sine of x differentiates to hyperbolic cos of x. And cos of x differentiates to minus sine x. And lastly, hyperbolic cos of x differentiates to positive hyperbolic sine of x. It's the only difference with the hyperbolic versions. Then we can collect those together, cancel the bits that cancel. We get minus 2 sine x times by hyperbolic cos of x. So for the third differential, product rule again, sine x differentiates to cos x. And hyperbolic cos of x differentiates to hyperbolic sine of x. Okay, can't do anything else with that, so we differentiate for the final time. Cos x differentiates to minus sine x, so I'll cancel with the minus out the front. Hyperbolic cos of x differentiates to hyperbolic sine of x. And then product rule once more, sine x to cos x. And hyperbolic sine x to hyperbolic cos x. Then collect everything together. Two of those will cancel. We're left with minus 4 lots of cos x times hyperbolic sine x, which is minus 4 lots of the original equation, minus 4y. So here k must be negative 4. Then for part B, the Maclaurin series, just for reference, useful to know sine of 0 is 0, cos of 0 is 1, hyperbolic sine of 0 is 0, and hyperbolic cos of 0 is 1. Okay, so our Maclaurin series for y using the Maclaurin series formula, f of x is equal to f of 0 plus f dash of 0 lots of x plus f double dash of 0 over 2 factorial lots of f x squared plus etc etc etc, and then the rth term will be the rth derivative of f of 0 all over r factorial lots of x to the r, and so on. Okay, so for our particular function, if we do f of 0, cos of 0 times by hyperbolic sine of 0, well, it's going to be 0. And then I plug 0 into the first differential and I get 1. Plug 0 into the second differential, I get 0. If I plug into the third differential, I get negative 2. Substitute it into the fourth differential and we get 0. And substitute it into the fifth differential and we get negative 4. So our Maclaurin series is going to be 1 lot of x, subtract 2 over 3 factorial lots of x cubed, subtract 4 over 5 factorial lots of x to the 5, which simplifies to x, subtract a third x cubed, subtract 1/30th of x to the 5. And there we go. Question number 9. So we're given y equals arc sine of 3x. I want to differentiate it. First thing I'm going to do is apply sine to both sides of the equation. So sine of y will be equal to 3x. If I differentiate both sides, sine of y differentiates to cos of y times dy by dx. That's going to be equal to 3. Divide both sides by cos y. I'll get dy by dx equals 3 over cos y. Cos y is the same as the square root of 1 minus sine squared y. So I'll replace my cos y with root 1 minus sine squared y. We know that sine y is 3x, so I can replace my sine y with 3x. When we square 3x, we get 9x squared, so it's going to be 3 over the square root of 1 subtract 9x squared. And that's dy by dx in terms of x. For part B, we're going to differentiate using the chain rule. So we differentiate the inside. Well, the inside of this function is arc sine of 3x, which we've just differentiated. So to find dy by dx, we are going to get the differential of the inside. That's 3 over the square root of 1 minus 9x squared, times by the differential of the outside function. The outside function is cos, so that's going to go to minus sine, so it would be minus sine of arc sine 3x. Well, minus sine of arc sine 3x is minus 3x, so 3 times minus 3x is minus 9x. It's going to be minus 9x all over the square root of 1 minus 9x squared. Okay. For part C, wants us to find the x-coordinate when the gradient is 4, so let's substitute dy by dx for 4 and solve the equation. So 4 is equal to minus 9x all over the square root of 1 minus 9x squared. Multiplying both sides by root 1 minus 9x squared, we get 4 lots of 1 minus 9x squared equals minus 9x. It's worth noting at this point that x must be negative, because otherwise we'd be creating an imaginary solution. So squaring both sides, 16 lots of 1 minus 9x squared is 81x squared. Expand out the left-hand side, 16 minus 144x squared is 81x squared. Bring the x squareds onto the right-hand side. 16 equals 225x squared. Divide both sides by 225. And then we want to square root that, so 4 over 15 plus or minus, well, we've already established that x must be negative. So negative 4 over 15, well done if you got that. Bye.